So angular momentum is not horribly difficult. So we're going to talk first about what it is. Um, so before and after the spinning jump, you will notice that they are really big. When they do a really tight spin, either a jump or just spinning on the ice, you'll notice that their body is much tighter together. And so for this one, you have a really big moment of inertia. You have a lot of mass far away from where you're rotating around. And then your angular velocity is small. You're not rotating very fast. In terms of the tight spin, once you bring your body much closer together, you'll notice that you have a much smaller moment of inertia because it is not very far from your outermost point to your center where you're rotating around in the middle of your body. And then your angular velocity is going to be really big. You're going to spin really fast. So, how does diving then relate to this as well? Well, first of all, you're going to push off of the diving board. And as you push off, you're going to apply a torque to cause yourself to start rotating. As you do so, you'll notice that she had her body super stretched out, which means you have a big moment of inertia. And she's going to rotate around her center of mass, which is about where your belly button is. For women, it's a little bit lower, and for men, it's a little bit higher, just because of the physiological way that your body is. And then here you're going to have that small angular velocity. You're not rotating very fast. But as soon as you leave that diving board, you want to have as many flips as possible, which means you want to make your moment of inertia smaller. So now you turn yourself into a ball. Now your center of mass is going to be more at the chest height, and you're going to rotate much faster. And then right before you enter the water, you want to have a small angular velocity. You don't want to be rotating really fast. So that's why you'll see the divers stretch out as long as they can, give themselves the biggest moment of inertia possible, and their angular velocity is going to slow down. So let's compare the two. So we've already done translational momentum, where momentum is equal to your mass times velocity. And the units were kilograms because mass is measured in kilograms times velocity, which is in meters per second. So that's how we get our units. We also talked about a relationship between impulse and momentum, where impulse is J, and that's going to be equal to your change in momentum. And impulse is force times time, and that's equal to your change in momentum. So it's not just about how much force you apply, but it's also how much time you apply that force for. And then when we talk about your change in momentum, momentum itself is mass times your change in velocity because your mass does not change. And so that's that side. Now we can do the same thing for rotational momentum. Here we have angular momentum. So angular momentum is capital L. Um, and it's going to be very similar to your translational momentum, but now it's moment of inertia instead of mass and angular velocity instead of velocity. So the units for rotational momentum, if you think about what rotational momentum is, or angular momentum, I mean, I is your moment of inertia, which is going to be kilograms times meters squared. Just think about the basic moment of inertia equation where it's mass times your radius squared. So that's where you get kilograms and meters squared. And then angular velocity is your change in angle divided by time, which is seconds. And if you did impulse versus angular momentum, instead of applying a force, you would apply a torque over some amount of time, and that would change your angular momentum. So if I take my change in angular momentum here, then I can put that into moment of inertia times my change in angular velocity. And so this is how you would put together torque, time, moment of inertia, and your change in angular velocity. So here we have that same skater that we looked at in the first place, and now I want you to pay attention to where her mass is in terms of how close she is to where she's rotating around and how that affects how fast she spins. And think about that relationship between moment of inertia and angular velocity. So next we're going to look at an example where we have a kid running tangent to the circle. And this is important because it is not really super clear what's happening. If I take this picture right here like this, I don't know if the kid is running straight at the circle or if she's running around the edge of the circle. Like I can guess, but I'm not sure. So think about it as if you aren't sure either. So if I think about this in terms of my translational momentum, I would say she was moving in a straight line before. And afterwards, she's going in a circle, which she would have some velocity going in a circle, but the whole thing is like the merry-go-round itself isn't moving anywhere. It's not translating. It's rotating, but it's not translating, which would mean that there's no translational momentum. So we're not even going to worry about this part. In terms of rotation, as she runs in, we're going to assume instead that she's running around the circle at that speed. And so you can use the relationship between translational velocity and angular velocity to determine what her angular velocity would be. And then you would then be able to use conservation of momentum to see how fast her and this merry-go-round will be going after she jumps on. So, in other words, translational momentum is not conserved. And the biggest reason is the center of this merry-go-round is going to apply a force, otherwise, the whole thing would slide away. Whereas rotational momentum is conserved because you're talking about something rotating, being this little girl. And then afterwards, both the girl and the merry-go-round are going to rotate. So, the really important thing here to know is that you can add types of energy, but you cannot add types of momentum together. So never ever add angular and translational momentum together. Another thing to notice about this is if I look at the units and the equations, all of my energy is going to be in units of joules. Rotational energy is also in units of joules. So it makes sense if I add joules and joules together that I will get joules. And so I can add these. But if I compare my angular momentum units to my translational momentum units, my momentum is mass times velocity here. So mass is kilograms, velocity is meters per second. In terms of my angular momentum, moment of inertia is going to be kilograms times meters squared, and angular velocity is that change in angle divided by time, or theta over seconds. And these are not the same units at all. So here I have kilograms times meters divided by seconds. Here I have kilograms times meters squared times an angle in radians divided by seconds. Now the units for the radians will go away, but the issue is that it's meters versus meters squared. So you cannot add these together, ever, or you will get the wrong answer. So these are not the same units. So what do you have to do? In terms of translational momentum, you can't use this because you're going to have momentum of the girl before. I have no idea what forces are being exerted from the center of the merry-go-round. It's just going to make her stop. I don't care about those forces. So I'm just not even going to worry about it. So we can use conservation of angular momentum for this problem because I can find the angular momentum of the girl. It'll be the moment of inertia of the girl, which will just be like a ball going around in a circle. So that'll be mr squared times the angular velocity of the girl, and then add it to the moment of inertia of the merry-go-round times the angular velocity of the merry-go-round. And then if there was a torque, that was causing a rotation, I would put that here. And then that would just be my torque times time, because this is impulse. And then after the girl will have her moment of inertia and her angular velocity after she jumps on, and then the moment of inertia times the angular velocity of the merry-go-round after the girl jumps on. So this is kind of the way to set it up, and then you just need to plug in your different moments of inertia. The only thing to be really careful of here is that your moment of inertia can change. So if you are doing the same type of problem, but think about your ice skater from the beginning, you would only have the moment of inertia, you would only have the angular momentum of the ice skater at the beginning, the angular momentum of the ice skater at the end, and the moment of inertia would change from the beginning to the end as they bring their hands in or as they put their hands farther out. And that would result in their angular velocity changing. Let me know if you have any questions or things you need clarified. Otherwise, good luck.